Hello everyone and welcome back. So in today's video we're going to do Vexercise, let's say, where we will create these poke faces digital assets, basically creating this kind of effect of poking faces. It's nothing too exciting, but hopefully you'll learn a few techniques, so let's get into it. So let's start by dropping a geo container, and I'm gonna create a grid. 10 by 10 is fine, we can just reduce the rows and columns to 8. And let's do the poking of the face. We don't have a SOP to do poke faces. There's one from the modeler toolset. I'm gonna also show you that. But let's do it in a traditional way. So if we group the edges, and then we do an extrude, and we do an inset of the individual elements, and there you have the poke faces. Now we do a simple fuse, and after that we can also group again. We still have that edge group, so of the grid. So now if we do edges and name it the same way, and we do include by edges unshared, and we do subtract, we get the interior ones, and then we can just dissolve, and we dissolve the group one, and we get the final result. So this was pretty easy. What's the problem with this? This can be really slow. So let's increase this. Let's try this. Let's increase to 256, and now let's test it. And as you can see, the extrude node itself takes a long time, and the fuse also. So if we actually test this, let me grab the performance monitor and let me record. Gonna pause and do 256 again, and let's unpause and let's wait. And as you can see, the poly extrude itself took about 2.5 seconds, so you can see, and the dissolve is also slow, and the fuse too. As you can see, this is really slow for working with high poly geometry. So of course this is the same way of doing poke faces. You can also try the modeler one, so poke, and let's reduce this again to 10 by 10, and we can try the poke, and it works. But if we increase these also, so let me open the performance monitor, always on top, and let's just do 256. Let's record. And this digital asset is locked, so it's black box, so we can see what's inside. But here you can see he's also using edge collapse and poly extrude, and it's also taking a long time, so 2.6 seconds, about the same. So what are our options? Our options is to do it with Vex, and that's what I propose today, to do a little exercise on doing this in Vex. So let's reduce that 10 by 10, and let me go to the performance monitor and delete everything. So let's keep this here, so traditional way, and now let's do a wrangle. So in order to create geometry in Vex, we need to rebuild everything again. So we need to rebuild the geometry. So we need to pass this to the second input, so we have no geometry coming. Or you can do it with a primitive wrangle, it can also work, but then again, it's about the same. So I'm gonna set this to numbers and do n prims 1, which is the amount of prims we're going to create. We're going to iterate through all the prims, so 81 prims in this case. And let's try to do this. And I'm gonna reduce this. I'm gonna reduce the polygon size, the polygon rows and columns to be about 2 and 2, so just one face. And then we're gonna create in here the poke faces. And let's color this. So yeah, the first thing we need to do is to get the prim point, so each point of each prim. So we can get that with a variable called points, and we just do prim points input 1 and I at lmnum. So this lmnum is just the iteration number, and it will match the prim num. So since we're iterating over all the prims, so lmnum. Then we need to grab the center of each prim, because we will create a point in the center and points at the edges, so we can later create the different polygons. In this case, 4 triangles for each face. So for that, I'm gonna grab the center, which will be vector center prim uv, and we just want to grab the center. So for that, I'm gonna grab the position, of each prim, lm num, and what position is that? So the center, and the center, it will be 0.5, 0.5, and 0.0 on the z-axis. So this is the intrinsic UVs. We can test that. So if we do int center pt, we can just add 0.0, and the pause is center. So the position is center, and it should add a point in the center, as you can see. So we're good, and it's just adding 1 point. If we change the amount of prims, so 5 by 5, it will create a point for each one. Let's keep it 2 by 2. The next step is to iterate over the amount of points we have in here. So in this case, we have 4, and create a point for the left corner of the triangle and one for the right corner of the triangle. So let's just create a variable here with the length of the points. I'm going to call it n, and it will be length of points. In this case, it's just 4. And then I'm going to do a for loop. Let me increase this. So I'm going to do 4. Gonna initiate the iterator, which will be called I, and I'm just gonna set it to 0. Then while I is less than the number of points, we will keep iterating. So I plus plus, adding 1. Let's open these. Now we need to grab the point position of these 2 points. So for that, I'm gonna just say int point 1. It will be from the array of the points. I'm gonna grab the current one, so with I. And then for the second one, int point 2, it will be points. It will be just the next one, so we can do points. And we're gonna grab the current one, I plus 1, and we need to wrap it around, so we just do modulo n, which is the length of the points, and that's the next point. And if we grab those positions, so vector pos 1, it will be equal to point, and we'll grab it from the second inputs, and the position and the point number, it will be 0.1. And we do the same for the second point, so this is pretty simple. So pos 2, it will be 0.2. And now we just need to add the point, so int new one, it will be add point, and we will add to the current input pos 1, and we do the same for the second one. And new 2, it will be pos 2. And as you can see, it's adding all those points. And it's adding, so if I select in here, it's adding 2 points on each corner. So because we need the current one and the next one for each triangle. And now it's pretty simple, we just create a polygon. So int 3, it will be equal add prim, and we want to add a poly, not a polyline this time. And that's fine. Now we should have 4 prims in here, as you can see. Now we just need to add the vertices. So, or you can input in here the point numbers, but I'm just gonna do int vertex 1. It will be equal to add vertex, and we'll add it to the current input, to the 3 primitive, and we just do new 1. Then we're gonna do the same for the new 2, and the order in here is important, otherwise we will get flipped polygons. Let me just do vertex 2 and vertex 3, and in here it will be the center point. So order here matters. And as you can see, we have now 4 polygons, and we're creating the poke effect. So that's done. And now the problem is we have the faces separated, or the prims separated. If I do an exploded view, and I do point, why the exploded view is not working? So if I do, so let's just drop an attribute, enumerate, and we'll do a primitive index, and we do in here index. So as you can see, we have points for each corner, so they are separated. So that's pretty simple. We just do a fuse, and we do a snap distance as small as possible, and we get this. And now if we increase this, we should have the poke effect working, because we're iterating over each prim and doing what we need to do in here. So now, how do we get rid of these initial lines? Because we can't really transfer in here the group from the initial grid, or we could, but let's do it other way. And also this fuse is slow, so we will look at other nodes that can do the same job. For now, let's work on the group of these geometry. So we want to select first this, let's keep the fuse and let's select this inner triangle. So how can we do that with Vex? Since this is a Vex exercise, we will do it with Vex. So let's create a wrangle and I'm gonna name it select trees. And this one, it's pretty simple. So we just need to grab the points that have a certain number count, a neighbor count. So in this case, these center points have a neighbor count of 4, and these ones have more. And then we can just find the neighbors, and that should give us that group. So in a point wrangle, we will do int count, and it will be equal to neighbor count, and we grab the point number. And now we do int names and an array, and these will be the neighbors. And we get from the point number also. And now we say if count is equal to 4. So these center points of the poke faces, we do a for each, and we will iterate over each neighbor in point nays. And we just do set edge group, and for edge groups we do the input, the name, edge trees, and then we do the 2 points of the edge. So in this case it's point number, the current point, and the point we're iterating, and we just set it to 1. And now if we grab that and set in here on the output selection, we have the interior edges selected. Now, in order to do the same thing we did in here, we did the solve, we also need the unshared edges. And we could also grab it pretty easily with a group node or with the unshared labs. So unshared, this labs node, which works pretty well. But let's do it with Vex. Since this is a Vex exercise, we will do it with Vex. So let's create a wrangle. And this one will be called unshared. And let's give it a color. And for the unshared, we could take advantage of the half edge functions. So I'm gonna grab the neighbors again. So int nays, it will be equal to neighbors incoming geometry and point number. So this just grabs the neighbors of each point number. And then we will iterate over for each. We will do int point, and we will iterate over the neighbors. Just open the bracket. And now we can grab the point edge. So int edge, it will be equal to point edge, and we will grab using the current point number and the neighbor. So we're grabbing that edge, and we will count in here the equivalent edges. So edge equiv count, and basically this function will tell us if this is an unshared edge, an interior edge, or even manifold. There are many outputs from this function. So if it is unshared, we know from the docs that the count of this edge is equal to 1. So this it will always be an unshared edge. So we can just set edge group, and we will call it unshared, and it will be from the current point number to the neighbor, and we just set it to 1. And now if we output this group, we should have the unshared edges, as you can see. So now it's pretty simple. We do dissolve, and in this case we can just set the 2 groups. So we dissolve, and we set in here the edge trees and the unshared, and dissolve non-selected, and we get the same result. And now let's see something. Let's set this to 256, and we go to Windows Performance Monitor, and we record. So I just need to grab it again. And as you can see, this took about 3.2 seconds. Let's stop and record again, and let's look at this one. So this one only took half a second, and most of it is with the fuse and with the dissolve. So if we didn't dissolve, let's just test this. So let's record, and just it in here, and it was in, sorry, I didn't record, so let's do this again. Record, and let's do this, and as you can see, only the selection is doing is taking a little bit of time, but it was pretty fast overall compared to these nodes. As you can see, it's still doing it, and to the poke one. But again, I'm sure Alex has better knowledge than me. He just did this for a reason, probably to preserve groups and whatnot. But anyways, so as you can see, our setup is working pretty well. And now let's do something to actually improve the performance. Unfortunately, I didn't find a way to replace the dissolve node. So maybe you don't even need it since you have this, but there's a way to replace this fuse node that also takes a little bit of time to compute. So let's do that in the next part. So basically now we need to replace this fuse node, and there is a node in Houdini that can do that, a low-level node. But before we use that node, we need to access what we have in here. So we have basically duplicated points on the corners, and we need to fuse them somehow. And in order to fuse them, we will need an attribute that tells us that these points that are on top of each other will have the same ID. So we need to give an ID to these points. And in order to do that, we will create what is called an hash. So let's create in here an hash ID, which will be more reliable for what we're going to do. So let's create in here that. And for that, I'm going to use an integer and call it hash a. And it will be an integer. And we will do random f hash, random f hash, and we will do it in based on not the point number, because we got different point numbers on top of each other, so we can't do that. We need the same ID for this point, so we will do it based on position because they share the same position. But the thing is, one hash, it won't be enough because this can have duplicated numbers depending on the amount of geometry you have, so we can do a second one. And this will be pretty simple. We just do HB and we just add a random number in here. So 234.4, something like that. So now we have two and we can combine it in a string attribute. So s at hash ID, it will be equal to concat, and we will convert this integer hash a to a string, and we will add an underscore, and then we can do the same for the hash b. So we'll combine both in a string, so hash b. And now we're almost 100% sure that this has a different hash on the points, a different identifier. As you can see, we're combining one with the second one and whatnot. So that's fine. Now each point in here shares the same ID. So if I actually show that, and how can I do this? So if I do an exploded view, and it will be difficult to see, but hopefully you see it in here. Or if I select in here these points and look at the geometry, and they should be highlighted, so this one and this one share the same hash ID, as you can see. And now we just need, in order to use the nodes that we're going to use, we need to just have one of the points without the hash. So basically we will do the following. We will create another wrangle in here, so attribute wrangle, and we will find that hash ID, so int index or point, we will find the point, so we find attribute val, and from the first input, and it's a point attribute, and it's called hash ID, hash underscore ID, and the value, it will be s at hash ID. So we find that point, and then we exclude it from the group that we're going to create and the attribute. So if index, so if the point we found is not the current point number, we just do the following. We group those points. I at group equals to fuse 1, and I at target point, it will be equal to index. And this will give us an attribute that basically tells us which point should I fuse this point 3, for example, I know that I'm going to fuse to point 2 and so on. So this point 12 will be fused to point 11, but we'll keep this point, so point 11, which is the first one we found in here, because this gives us the first output of the, or we can do it with an array and find all, but in this case, this one will work. So this will be called target rewire. And the node that we're going to use, so let's just keep these in here. And the node that we're going to use is called rewire vertices. So if you notice, we also have in here a fuse group. So let's see, and it's basically selecting all but one point, which will be the target point. So now we can do the following: we can rewire this, and this needs an attribute that is called target PT, and we also need a group, which is this fuse. And as you can see, we end up with 113 points, and if we do the fuse, we get the same result. And this is our custom fuse, and it will be much faster than the fuse. Only the dissolve node is the slow one, which I don't know how to replace. I try to do it with this rewire, but this node just rewires vertices, so it doesn't really get rid of prims, because in order to remove these edges in here, we need to get rid of some prims. So I don't think we can actually do that with the rewire, but again, I don't know, it's the first time I'm using these rewire nodes, so I'm not sure it can do it or not. So yeah, again, we already tested the performance, we don't need to do the same again, but basically these will be much more performance than the default option of doing the poke faces. So yeah, again, guys, this was a very nerdy exercise on how to do poke faces in Houdini using Vex, but you can see how these will scale up if we start to implement some things in Vex. Some things work faster most of the times with Vex, but not always, so you have to experiment with it. But in this case, doing these geo operations and fusing, it's quite slow in high poly geometry, so always try your options. In this case, it's much faster, as I showed you in the performance monitor. Again, guys, if you want to check out my Patreon, I have hours and hours of exclusive tutorials there, all the project files from my videos, including this one. And if you found this interesting, please leave a comment below. And as always, thank you for watching, and I'll see you next time. Thank you.